What I'd like to talk to you about today is using graph-based deep learning for reasoning about programs. So just to give one slide, how can I change slide? There we go. Okay, just a one slide introduction to myself. Yes, I work at the intersection of two fields which historically have had quite little to do with each other. So compiler research and compiler engineering and machine learning research. So this gives my job title a very nice circular definition because I do machine learning for compilers for machine learning. But yeah, so historically, like I said, not much in common typically between these two fields. So to give a little overview of why I like this, and I should just preface this by saying that Saman has done an excellent job of building the case for machine learning compilers previously in the talk. So I guess I can go through this a little bit more rapidly because hopefully you should all now be convinced that machine learning is the way to go for compiler construction. But the way I see it is that the task of tuning, optimizing compilers is like the ultimate job for life because it's like this Sisyphean task because compilers are so complex. The range of features that they need to support, the hardware they need to support, the different, obviously like the infinite space of possible programs that you could feed into them. It's a very challenging task to figure out how to tune all of those thousands of dials within a compiler so that you get the best performance out of your silicon. So typically the way this is done in production compilers is through total black art. You get some very, very clever compiler engineers to spend an awful lot of time trying to figure out how to tune these optimizations to give them the best numbers on the benchmarks. So it's very much limited by domain expertise. And this is challenging because the time of compiler engineers is very precious. There's a lot of work to be done. And the compiler and the hardware keeps changing. So actually just trying to keep up with this rapidly changing ecosystem would mean that you would basically be doing nothing except trying to do compiler tuning. So the cost of this is obviously we just have bad heuristics. Compilers have stale heuristics. They're often out of date before the compiler is even released. This is obviously a bad thing. We waste a lot of energy. That costs money and also the environment. And what we've seen in the last few years, especially, or for quite a while, is this kind of widening performance gap between the theoretical performance that our silicon can offer and what our compiled code actually achieves. So what can we do to address this? Well, how about if we can turn the entire activity into a data science problem? So rather than trying to figure out how to tune our compiler to give us the best possible performance under all scenarios, we'll instead collect a bunch of examples. And an example here is some program, some representative benchmark, plus some empirical measurement of what was the best optimization decision to make. And we're going to take a bunch of these examples and then we're going to try and learn from them to give us our heuristic. So if we can learn to capture, the correlation between the benchmark and the optimization decision that can be made, then we've effectively automated the job, which is nice. I'm always trying to automate myself out of a job. But it also means that when the compiler changes, and it does quite frequently, or when Intel comes out with a new set of hardware or there's some new backend that you're trying to support, this is an automated process, so you can just repeat it. You can just run the same scripts or run the same experimental setup, and you get yourself a new heuristic. Okay, so just to go into now just the very high level, the details of how this is going to work. The first thing we're going to need to do if we want to learn how to optimize code is we're going to need some way of summarizing the program such that a machine learner can understand it. And the way that this is typically done is you take your code, you take your program, you then drop it down to an IR, so it could be some kind of control flow graph or data flow graph, or there's a line of work that uses ASTs. And then you're going to extract from that IR some vector of numbers which describe the program, the features. So typically these features are counters. Essentially, you'd go to your IR, you would look at all the nodes and you would say this is how many instructions. That could be a feature, or it could be how deep are your loops, or what is the density of like arithmetic instructions? How much are you going to hammer the ALU? Or if you are lucky enough to know, like, what are your loop bounds? And the idea is we take this summary of the program and we're going to collect a bunch of them from enough different programs combine those with the best parameter, like whatever it is that we're trying to optimize, we just measure that. And then if we can get enough of that data, we're going to try and turn that into a supervised machine learning problem so that we can learn a model. So a model in this case is simply this curve. It's the thing that says when you get a new program that comes in, you're going to map it into that feature space, and based on that model that you learned on your prior data, it's going to estimate for you what is the parameter, what is the optimization decision that you should make. And the idea is, if we can do this, then we take, if we can train a model to high accuracy, high performance, we've shoved that model inside the compiler, and that replaces the traditional hand-tuned heuristic. Okay, so like I said, someone gave a great talk about this. This is a very, very successful approach for tuning, optimizing compilers. There's a huge number of research papers that have been trying this in various different isolated environments. They typically find that supervised machine learning outperforms human experts, which is great. And the performance gains that can be had are real. So if anyone's interested, I'd refer them to one of the 2 recent survey papers, which kind of give a broad strokes overview of the area. Okay, so it sounds like a solved problem. So then the question is, why aren't our compilers full of machine learning? So there's a number of issues with this, or there are a number of real interesting challenges that I think we need to overcome. The one I'm going to focus on in this talk is the features. So it turns out that picking the features, picking the way in which you're going to characterize your program for your model, is very, very hard to do. So let's take a little detour, just a tiny little one slide recap into kind of the deep learning world. So fairly recently, I think the paper that I published in at this conference, actually at PACT in 2017, I think was the first use of this, although now there's lots and lots of them. So I proposed this idea of learning without using features. And the idea was, we're going to, instead of taking the program and lowering it down to an IR and then inspecting the IR, we're instead just going to feed that program through a natural language model and see if, based on that, we can classify that into some optimization decision. So the idea is you've got your input, which is the string of your code. You then have to put that into some kind of vocabulary, which is basically just a table. And so for this work, I used a table of OpenCL keywords. And that gives us an encoded representation, which is basically just a long string of numbers showing you, what elements in the vocabulary occur in the program. Feed that through an LSTM, which is a very popular recurrent neural network, and then from that produce a prediction for optimization heuristic. So the results of this was great because it means you don't have to do feature engineering. But the problem with both approaches, trying to reduce a program to a vector of numbers or trying to learn over a sequence of text, is that none of them really get to the essence of what is software. Like, source code isn't a flattened vector of numbers. Feature vectors are so easy to fool. If all you're doing is counting instructions, you just throw a huge chunk of dead code in, and all of a sudden your feature vectors go whack and the model goes crazy. But also, code isn't actually a sequence of text. How many people, when they're trying to understand a new program, start by reading it one word at a time from top to bottom? You don't do that. Code is super non-linear. It's like recursive. It's got this really rich hierarchy to it. And natural language models, the models which read text one token at a time, often fail with this. They obviously, because they're going in a order, they can't see things that haven't yet occurred. So the non-linear relations are lost. But also the long-range dependencies. So LSTM recurrent neural networks theoretically have an unbounded length through which they could learn some interesting signal over time. But in practice, I think there was a paper where they evaluated it on a bunch of different problems and found that it was about 1,000 time steps before an LSTM has forgotten anything. So if your program contains more than 1,000 words, and most programs do, your LSTM's already forgotten what it started looking at by the time it gets to the end. So we have an issue. And the paper that I'm plugging at this talk is trying to address this, or trying to tackle this problem by thinking, well, what if we can make machine learning think like a compiler? So by that I mean, what can we produce an input for machine learning that actually more closely resembles what our compiler sees when it is actually making the optimization decisions that we care about? Okay, so we came up with, so I should also credit, of course, my co-authors. So this is work that I did with ETH Zurich, with Zach and Tal and Torsten, and also Mike at the University of Edinburgh. And what we came up with was program graphs for machine learning, which is a horrible name because you can't pronounce the acronym ProGraML. But I mean, I don't know, I'm not very good at naming things. But the idea of ProGraML was it is a general purpose representation of programs for doing optimization stuff. So when I say stuff, what I mean is we didn't want to specialize our representation to a specific task. Because often if you look at something like the features that you might use for, say, predicting loop unrolling, they would be totally different from the features that you would use for, say, inlining. So what in the kind of research, you look at all these papers, you look at 10 papers and you get 10 different feature sets. So we wanted one representation that we could use for all different problems. So to do that, what we wanted to do is we want to capture the relationships in programs, or the relations in programs that are fundamental to reasoning about programs. And for that, the kind of benchmark is data flow analysis. You know, there is already this well-established formalism for how compilers can reason about programs. So data flow analysis seems like a good yardstick for machine learning. The idea being that if machine learning can't do data flow, then why would it be able to do any of the other optimization tasks that depend on data flow? The third thing about ProGraML is that it's language independent, and we did this by targeting a compiler IR rather than a specific source language, because again, there's a lot of source languages. Okay, so I'm going to briefly go through the steps of what ProGraML looks like, start by just using a very simple example program. So in that yellow box is about the shortest program that I could think of which does something interesting. So we've got your classic recursive Fibonacci. It's your whiteboard job interview algorithm. And what we do is, to build ProGraML, we start by lowering it down to an IR. So in this case, we've so far focused on LVM IR, but the approach is actually general for different compilers. So we also have support for XLA, but we just haven't got around to doing anything exciting with it yet. So the reason for choosing the IR is the obvious one is that it's language agnostic. If you get a compiler like Clang, or compiler like LVM, where they've got lots of different front ends, then you can represent a large number of different source languages using this IR. So for example, with LVM, we built a dataset which is like C code, C++ code, OpenCL, Swift. Then it gets really weird. We've got like Haskell thrown in there. Some guy did a Java, added some Java programs as well. And we can tackle all this with the same representation. And then the other thing is that the other reason for picking an IR level representation is that we are trying to get as close as we can to enabling machine learning to think like a compiler. So we need to see what a compiler sees. So that's why we didn't want to choose a source language. Okay, so on the green box is the LVM IR that you get from this recursive Fibonacci. And then what we're going to do is we're going to take that and we're going to build a graph. So the graph we're going to build is a control flow graph, a full flow graph actually, rather, in which every single instruction becomes its own node. We're going to give those nodes a label, which is the name of the instruction, and then we're going to connect all those nodes up based on their control flow. The other thing is that the edges have a numeric attribute for branches. So for example, that switch, which has got 3 guys coming out of it, by adding a number, by adding like a tag to those edges, you can tell which branch was which. Okay, so once we've got the control flow, we're then going to throw in data flow. So for data flow, what we're going to start by doing is we're going to take all of the variables and all of the constants in the program, all of the unique variables and constants, and we're going to create a node for each of them. So in this case, we've got these red, which have I chosen? Diamonds for constants. So red constants and red oblongs for variables. And then we're going to go through the instructions in the program and just connect up all of those variables and all those constants to all the instructions that use them and all of the instructions that write to them. And what we end up is with this nice little union of control and data flow. And again, we've got a numerical attribute on the edges, but this time this is used for showing operand order. So for example, if you've got add or say divide, A and B, you'll have two different numbered edges going in. So you can tell which one was A and which one was B. Okay, so then afterwards, we've got call flow. So call flow is basically the throw in a call graph. So you take all of the function calls, the instructions that do function calls, you figure out the entry point for the functions that get called, and you throw in a call edge, which is one of these green lines. And then in that function, all of the return statements, all of the points at which the function terminates, you then connect those back to the guy that called it, and that gives you a way of tracing through the call graph, through the control flow graph. Okay, so we're nearly done, and the graph is starting to look a bit complicated. The final thing we did is we also wanted to represent types. So we threw in a type graph. So what we did is we took, you take all of those variables, all those constants, and let's say they are int32s, like they are for Fibonacci, where you create an int32 node, and then you connect that up to all the variables and constants that use it through these type edges. So in the Fibonacci example, it's not very exciting because there's only a single type. But the important thing here is that we actually decompose types into their own little graphs. So in the bottom left, I've drawn what I think is a more interesting example, which is a nested struct, or a struct which references itself. So for example, this could be like a linked list implementation. And the way that would look in our type graph is you've got a struct, you've got a type for the element number 1, type for element number 2, and those guys connect up to the struct, and then you've got a pointer, and the pointer self-references. Okay, so that's pretty much about everything we could think of that you need in order to represent a program. So now what are we going to need to do is we're going to need to turn it into something that you can do machine learning on. So to do that, we need to turn all of those strings, the labels, which are the names of the instructions and the names of those types, and we need to turn them into numbers. So we do that using a vocabulary, which maps to an embedding being a real vector, a real valued vector, which just allows you to say do semantic grouping or learn semantic grouping of similar elements in the vocabulary. So what we do is we take every single one of those unique strings inside those nodes, we map each one of them to a unique element in the vocabulary. And what this means is that we're deriving a vocabulary based on some set of training graphs, rather than specifying it by hand. And the nice thing is, because we've got this graph in which we've basically pulled everything apart, like an instruction is separate from its operands, is separate from its type, because of that, we actually don't need a very big vocabulary to get incredibly good coverage over programs. Because there's this issue with machine learning where you're trying to represent a program in which what happens when you get a word that you've never seen before. Like what if someone's created a new type, or someone's used an instruction that you've never seen before? Well, normally what you do is you just map it to some element in your vocabulary that you've reserved for saying, this is an unknown element. I don't know what this guy is. It's just it's unknown. But what we found is that because we've split apart our graph, a small vocabulary is good enough to give us near perfect coverage on unseen programs. Then there's an asterisk on this little table here because this is actually from an earlier version of ProGraML before we added the type tree. So this is why we've got 1.7% of elements are unseen. Those are user-defined types that we didn't see in the training graphs. Our coverage now is 100%. So in this table we compare it against two prior approaches. InstaVec is a great paper from NeurIPS 2018, I think, which is a way of taking an LVM IR statement and mapping it into an embedding. But because what they are doing is mapping an entire statement to an embedding, there is an infinite number of statements, so their vocabulary coverage is really poor. And another representation, which is CDFG, which came out, I think, this year at, I want to say CC conference, which is great. It's a graph representation, but the problem is they just don't include everything that you would want to represent the program. So they don't include types, they don't include variables, they don't include operand order. Okay, so the way in which we process these graphs is using gated graph neural networks. Now, I'm not going to try and go into the equations, but suffice to say, this is pretty much off-the-shelf graph neural networks, which were developed in, I want to say, about 2015 in MSR by Eugene Lee for doing, I think it was biochemistry at the time, and then they've become massively popular because it turns out that graphs are really useful as a way of representing data. So we took their approach, or we took their model architecture. We did make two small adjustments. The first is we threw in this position gating, which is basically borrowed from the transformers. It's a way of telling apart different operands. And the important thing is what we get out of this in the bottom equation is we can either produce a prediction for every single node in the graph, or we could do a prediction for the entire graph. So what this lets us do is full program prediction, which is kind of like what we would do traditionally with machine learning, where you take a program, you extract a feature vector, and then you try and predict some property on it. But also, because we can do per vertex prediction, we can do some really nifty new things, like we can try and predict individual instructions that might be amenable to a certain optimization. So the application that I want to describe to you guys that we tested this on, or one of the applications, is to learn data flow analysis. So the idea here is that we've got this family of data flow algorithms. Anyone who's done a compiler course at university will remember these guys. You have to learn those two equations for transfer function and meet function. They are basically the fundamental building blocks for how compilers think about programs. And any compiler will contain a really great quality implementation of these guys. So what I wanted to do is I wanted to take these really well solved problems, and I wanted to instead see if we could throw machine learning in to try and replicate them. Can we learn reachability? So reachability is, given some instruction in a program, can you just tell me all the other instructions that you can get to? And what's remarkable about this is that prior approaches really struggle with it. Like InstaVec, being an LSTM-based approach, very much struggles with nonlinear representations. It can't see that an instruction is reachable until you've actually gone to it. Can't see into the future. And then we tried like dominators. Again, this is kind of a classic data flow analysis. We did data dependencies, which is basically given a variable, tell me all the instructions you need in order to compute it. That's basically the heart of data flow graphs. And then did live out analyses. And then the one that I really liked was global common subexpressions. So given some instruction in a program, label for me all the other instructions which basically do the same thing, because you could optimize them, if maybe there's a way of optimizing them away or combining them. So these are already solved problems, but I think they make a really interesting yardstick for measuring the effectiveness of machine learning about reasoning about programs. So a couple of things to point out. Yes, we are the first representation which actually is powerful enough to do per variable predictions, which was nice. And now I want to go into the caveat of this approach. So a data flow analysis will iterate until a fixed point is reached. It's got two equations, and you basically just run through those two equations until you're done. With a gated graph neural network, what we do is we instead say, here is a starting graph, iterate on it for some number of time steps, which we fix, we call it t, and then you're done. So for every example in the training set, in the test set, what we did is we figured out how many steps a traditional data flow analysis would need in order to solve it, and then we just made sure that we gave our neural network enough time to solve it, which is a huge caveat. Like this is a case of where it means that our machine learning can only solve problems for which we already know the size of the solution. So in the previous slide, we had excluded about 30% of this data set, which is it's quite a large data set, but sorry, I should have mentioned. It's about 500,000 lines of code. 500,000 programs. It's about a fair few million lines of code. So what we then wanted to do is, okay, if we artificially limit the problem so that we know that a machine learner should be able to solve it, how does this scale? How can this work for inference? So this table on the right, where it says 30 time steps, that shows the result from the previous slide where we just fixed the number of time steps we do our gated graph neural network. And then the column to the right of it, 60 time steps. What we did is we took that model that we had learned, and then we basically just doubled the amount of inference steps it had. So we said, okay, you've learned a solution which works within 30 time steps. Now here's a problem that's twice as big, and here's twice as long to try and solve it. Go ahead, see how you can do. And then the final column is we scaled that all the way up to 200 time steps. So at this point, we were considering quite massive problems. So there's a couple of interesting things that I think tell us a little bit about not just how gated graph neural networks work and their applications to compilers, but also gives some kind of directions for future research into machine learning for program analysis. So the nice thing is that it shows that gated graph neural networks can scale well when we double the problem size, which is very useful because the problem with compilers is that you don't know how big your program is going to be, and you really don't want a compiler that's going to barf just because the program is too big. But what we do see, and a bit more worryingly, is that when we go over 6 times over the number of time steps that we've trained on, the inference performance just absolutely bombs. So what we observed by picking through individual examples is that our machine learned algorithm was no longer behaving like a lovely fixed point. It was instead kind of like over approximating on some problems and under approximating on others. So it seems like there's a disparity between what the function that the machine learner is learning and what a traditional, hard-coded data flow analysis would compute. Okay, so we're getting towards the end of my talk now. So I'd just say that we're not just interested in data flow analysis and solving already solved problems, because why would we be? What we actually want to do is, of course, use this approach to do reasoning about programs and reasoning for optimization. So we test this on a couple of downstream tasks. So the first of which was a algorithm classification task. So there's this lovely data set that some guys released a few years back, which is basically 104 different classes of program, and they've got like 50,000 examples in total. And your job is to try and predict for every program what is the class, like what does the algorithm do. And then this, our approach quite significantly outperformed the state of the art. And then the second downstream task that we looked at was a optimization task, which is one of these cases where you've got an entire program. Your job is to try and predict for this program whether or not it would be faster to run on the CPU or the GPU. So in this case, you need to be able to try and learn to correlate the hardware characteristics, the hardware performance, against the properties of the program. And again, in this case, we found a nice improvement over the state-of-the-art techniques. Okay, so this is a paper that is, I would say it's very late stage work in progress, like we have not yet published, but we've got a preprint that's available if this is interesting to you. That link at the middle there takes you to a little website that I spent way too much time working on, which is a nice little flashy in-browser demo of the thing. So you go to the site and it shows you can type in a program and it will build the graph for it, so you can actually see how this graph is constructed from programs. It's all open source. It's available as of now, Apache licensed. Please do try it out if you are interested in any task for which you might want to learn to reason about programs. So a few kind of like concluding words then. So reasoning about programs, I think it's very important to get the right combination of representation and then a model which is capable of processing it. So ProGraML was designed like from scratch, combining all sorts of elements from compilers, control flow, data flow, call flow, type graphs, in order to give us the most comprehensive representation of an IR that has been so far used. And what we find is that the nice thing is that we take this representation, we process it using some off-the-shelf gated graph neural networks, and we get significantly better performance than prior graph-based approach and prior sequential-based approaches. So I think there's a bunch of interesting challenges that we kind of want to look at next. This is not by any means a solved problem. So I think just 3 of the ones that I think are most interesting. So first off is processing arbitrary sized graphs. By that I mean we need a compiler which accepts programs of any size. Programs can be very, very small, tiny little kernels or hello worlds, or you can get these monolithic apps. And at the moment, all machine learning approaches really struggle to scale with those very, very large graphs. So there's kind of two factors there. There's first off is the kind of the dull one, which is literally just fitting it inside a GPU, but that's fine. That's basically going to be solved by time. And the second one is figuring out how to process the graph in a way that more closely represents what a data flow solver would do. The second problem that I think is really interesting is handling unbounded vocabularies. So although we are able to get very, very good coverage on unknown programs, we don't yet have perfect coverage, because there is always the possibility that user program contains something that you've not seen before. A perfect example of this is what happens when we want to learn about literals. So for example, we're not going to have a vocabulary that includes every single possible string permutation in the C programming language. So I think this is an interesting open area. There's a bit of work that's going on in various different areas, not necessarily to do with programs, but I think that's going to have a big improvement in the next few years. Yes, so representing literal values and also thinking like a data flow solver. Okay, so that is the end of my talk. I'd be delighted to field any questions or insults, and thank you very much for listening.